What are DevOps best practices?
Key DevOps best practices include infrastructure as code, IIC, version control all infrastructure definitions for repeatability and auditability, continuous integration and continuous deployment, CI/CD, automate build, test, and release pipelines to deliver changes safely and frequently, monitoring and logging, collect metrics, traces, and logs so issues are detected before users are impacted. Automated testing. Unit, integration, and end-to-end tests act as a safety net for every change. Security as code. Embed security scanning, secret management, and policy enforcement directly into the pipeline rather than treating it as an afterthought.
What is the purpose of infrastructure as code, IIC?
IIC means defining servers, networks, and other infrastructure in machine-readable files. For example, Terraform HCL, CloudFormation YAML, Ansible playbooks. Rather than clicking through consoles. Key benefits, repeatability. The same code produces identical environments every time, eliminating works on my machine drift. Version control. Infrastructure changes are reviewed in pull requests and fully auditable via Git history. Faster provisioning. Spin up or tear down entire environments in minutes instead of hours. Disaster recovery. Recreate a lost environment from code rather than from memory or runbooks.
Why is version control important in DevOps?
Version control, most commonly Git, is the backbone of the DevOps workflow. Full change history. Every modification is recorded with who made it, when and why, commit message. Collaboration, branching strategies, Git flow, trunk-based development. Let multiple engineers work in parallel without conflicts. Code review. Pull requests enable peer review and automated checks before code reaches production. Rollback, reverting to a previous commit or tag, is the fastest way to recover from a bad release. Traceability. Links between commits, tickets, and deployments provide a clear audit trail for compliance.
What is continuous integration, CI?
Continuous integration is the practice of developers merging code changes into a shared repository multiple times per day, triggering an automated pipeline on every push. The pipeline typically 1. Compiles or builds the application. 2. Runs the full automated test suite unit integration. 3. Performs static analysis and linting. 4. Produces a versioned deployable artifact. Example GitHub Actions trigger.
Code on push pull request jobs sci runs on Ubuntu latest steps uses action/checkout at v4 run npm sci and npm test.
CI solves the integration hell problem. The longer branches diverge, the more painful the merge. By integrating frequently, conflicts are small and caught immediately, and the team always has a known good build.
What are the key components of a CI/CD pipeline?
A typical CI/CD pipeline flows through these stages. 1. Code commit, developer pushes to version control, triggering the pipeline. 2. Build source code is compiled and packaged into a deployable artifact, JIR, Docker image binary. 3. Test, automated unit, integration, and end-to-end tests validate correctness. Failures block the pipeline. 4. Security scan, SIST, dependency vulnerability checks, and container image scanning run at this stage. 5. Deploy to staging. The artifact is deployed to a production-like environment for final validation. 6. Acceptance/smoke tests, automated or manual verification that the release is ready. 7. Deploy to production, automated continuous deployment, or manual gate continuous delivery, release. 8. Monitor, dashboards, and alerts confirm the release is healthy. Rollback is triggered if metrics degrade.
What is the difference between continuous deployment and continuous delivery?
Both practices build on CI and automate the path to production, but they differ in the final step. Continuous delivery. Every successful build is tested and staged automatically, but a human must approve the production deployment. This gives teams confidence while retaining a manual control gate, useful when regulatory sign-off or business timing matters. Continuous deployment. Every passing build is released to production automatically with no manual intervention. This requires a mature test suite and feature flagging strategy, but enables multiple deployments per day and the fastest possible feedback loop. Most teams start with continuous delivery and graduate to continuous deployment as their test coverage and operational maturity grows.
What is the importance of automated testing in DevOps?
Automated testing is the safety net that makes fast deployment safe. Early bug detection. Tests catch regressions immediately after a change. When the fix is cheapest, studies show defects found in production can cost 10-100x more to fix than those found during development. Confidence to refactor. A strong test suite lets engineers improve code without fear of silent breakage. Test pyramid. Most tests should be fast unit tests, fewer integration tests, and even fewer slow end-to-end tests. This keeps pipeline feedback times low. Types used in DevOps: unit, integration, contract, end-to-end, performance/load, and security, SIST/DIST. Tests. Gate in the pipeline. Failed tests automatically block the deployment, preventing broken code from reaching users.
What is the purpose of monitoring in DevOps?
Monitoring gives teams real-time visibility into the health and performance of running systems. Core monitoring areas: metrics, CPU memory, error rates, latency, throughput, tracked with tools like Prometheus and Grafana. Logs, structured event records aggregated into platforms like the ELK stack, Elasticsearch, Logstash, Kibana, or Loki. Traces, distributed tracing, Jaeger, Zipkin, follows a request across microservices to pinpoint bottlenecks. Alerting, threshold or anomaly-based rules page on-call engineers before users notice a problem. The 4 golden signals from Google SRE. Latency, traffic, errors, and saturation provide a concise starting framework for any service. Good monitoring also enables SLO tracking, capacity planning, and post-incident analysis.
What are blue-green deployments?
Blue-green deployment maintains 2 identical production environments: blue, current live, and green, new version. How it works. 1. Deploy and test the new version in the green environment while blue still serves all traffic. 2. Flip the load balancer or DNS to route traffic to green. 3. If anything goes wrong, roll back instantly by pointing traffic back to blue. Advantages: 0 downtime releases, the switch is near instantaneous. Safe rollback, the previous environment is kept warm and ready. Full production testing before go live. Trade-off, you temporarily need double the infrastructure, increasing cost. Works best for stateless services, database schema changes require additional care.
What is the role of logging in DevOps?
Logging records discrete events emitted by applications and infrastructure throughout their lifetime. Key uses: troubleshooting, pinpoint the exact error, stack trace, and context when an incident occurs. Audit trails, required by compliance frameworks SOC2, PCI-DSS, to prove who did what and when. Trend analysis, aggregate logs over time to spot degrading patterns before they become outages. Security forensics, detect unauthorized access attempts, anomalous IP calls, or data exfiltration. Best practices, use structured logging JSON, include correlation IDTKS to link logs across services, set appropriate log levels, DEBUG/INFO/WIRN/ERROR, and centralize logs in a searchable platform like the ELK stack, Splunk, or CloudWatch.
What is shift-left testing in DevOps?
Shift left means moving testing activities earlier in the software development lifecycle, toward the left side of a timeline that runs from design to production. Traditionally, testing happened after development was done, meaning bugs were found late when they were expensive to fix. Shift left brings testing as close to the code change as possible. Practices that embody shift left, test-driven development, TDD, write tests before writing the feature code. Static analysis and linting run in the IDE or on every commit. Unit tests run locally before pushing. Security scanning, SIST, in the CI pipeline, not in a quarterly audit. Contract tests to validate IPI agreements between teams early. The earlier a defect is found, the cheaper it is to fix. Studies estimate a 10x cost increase per stage, dev, test, staging, production.
What is feature flagging?
Feature flags, also called feature toggles, are configuration-driven switches that control whether a specific feature is active at runtime without requiring a new deployment. Common use cases, gradual rollout, enable a feature for 1% of users, monitor metrics, then increase to 10%, 50%, 100%. /B testing, show variant A to half of users and variant B to the other half, compare outcomes. Kill switch, instantly disable a misbehaving feature in production without rolling back the entire release. Trunk-based development, merge incomplete features behind a flag so they don't affect users until ready. Popular tools, launch darkly, unleash, flagsmith, or simple environment variable checks. Flags decouple deployment from release, giving teams precise control over feature exposure.
What is immutable infrastructure?
Immutable infrastructure means that once a server or container is deployed, it is never modified in place. Instead, any change, OS patch, config update, new app version, triggers building a fresh image and replacing the running instance. Benefits: no configuration drift. Every instance is guaranteed to match its source of truth definition. Predictability: the exact artifact tested in staging is what runs in production. Simple rollback: revert to a previous image version rather than trying to undo manual changes. Easier debugging: you always know the state of an instance, and works on one server but not another, problems disappear. Containers, Docker, and VM image pipelines, Packer plus IMI baking, are the primary tools for achieving immutability. IIC tools like Terraform reinforce this model by managing instance lifecycles declaratively.
What are rolling deployments?
A rolling deployment gradually replaces old instances with new ones in batches, rather than taking everything offline at once or running two full environments simultaneously. How it works: 1. The orchestrator, Kubernetes, a WS code deploy, takes a subset of instances out of the load balancer. 2. Those instances are updated and health checked. 3. If healthy, the next batch is updated. If unhealthy, the rollout pauses or rolls back. Advantages: 0 or minimal. Downtime: most instances stay live throughout. Lower infrastructure cost than blue-green, no doubled environment needed. Automatic rollback on health check failure. Trade-off: during the rollout, old and new versions run simultaneously, so the IPI must be backwards compatible. Best for stateless services: watch out for database schema changes that are not backward compatible.
What is canary deployment?
Canary deployment routes a small percentage of production traffic, say 15%, to the new version while the rest continues to the stable release. The name comes from the canary in a coal mine metaphor, an early warning signal. Typical flow: 1. Deploy new version alongside the current one. 2. Shift a small slice of traffic or a specific user segment to the new version. 3. Monitor key metrics, error rate, latency, conversion rate for a defined soak period. 4. If metrics are healthy, gradually increase traffic until the new version handles 100%. 5. If metrics degrade, instantly redirect all traffic back to the stable version. Benefits: real user validation with minimal blast radius, data-driven promotion decisions. Tools: Argo rollouts, Flagger, a WS code deploy, Nginx/Envoy traffic splitting.
What are microservices, and how do they impact DevOps?
Microservices is an architectural style where an application is decomposed into small, independently deployable services, each responsible for a single business capability and communicating over lightweight APIs, REST, gRPC, or messaging queues. Impact on DevOps: independent deployments. Teams can release their service without coordinating with others, enabling faster iteration. Independent scaling. Scale only the services under load rather than the entire monolith. Technology diversity. Each service can use the best language or database for its needs. Smaller code bases. Easier to understand, test, and onboard new engineers. Challenges introduced: distributed systems complexity. Network failures, latency, and eventual consistency become first-class concerns. Operational overhead. Many services means many pipelines, logs, metrics, and alerts to manage. Service discovery, load balancing, and tracing must be built into the platform. DevOps practices like container orchestration, Kubernetes, service meshes, Istio, and observability platforms are essential to operate microservices reliably.
How do you manage secrets in DevOps?
Secrets, IPI keys, passwords, certificates, tokens must never be hard-coded in source code or checked into version control. Best practices: use a dedicated secret store. HashiCorp Vault, a WS Secrets Manager, Azure Key Vault, or GCP Secret Manager provide encrypted storage, fine-grained access control, and audit logs. Inject at runtime. Applications retrieve secrets at startup via environment variables or mounted files, not from the codebase. Rotate regularly. Short-lived credentials, for example, 24-hour tokens, limit the damage from a leaked secret. Least privilege. Each service gets only the secrets it needs, nothing more. Scan for leaks. Tools like Git Leaks, Truffalog, or GitHub Secret Scanning alert when secrets are accidentally committed. Audit access. Every secret retrieval is logged for compliance and forensic investigation.
What is GitOps?
GitOps is an operational model where the desired state of infrastructure and applications is declared in Git repositories, and automated agents continuously reconcile the actual state of the system to match that declaration. Core principles: declarative configuration. Everything, Kubernetes manifests, Helm charts, Terraform state, is defined in Git. Git as the single source of truth. The current Git state is exactly what should be running in production. Automated reconciliation. Operators like Argo CD or Flux watch Git and apply changes automatically. No manual kube control apply. Pull-based deployments. The cluster pulls changes from Git rather than CI pushing to the cluster, improving security. Benefits: full auditability, Git log equals deployment history. Easy rollback, revert a commit. Consistent multi-cluster management and reduced blast radius from compromised CI credentials.
Why is containerization important in DevOps?
Containers, Docker being the most prevalent. Package an application together with all its dependencies, runtime, libraries, config files, into a portable, self-contained unit. Why this matters for DevOps: environment consistency. The same container image runs identically on a developer's laptop, in CI, in staging, and in production, eliminating works on my machine bugs. Portability. Images run on any Linux host and across AWS, Azure, GCP, and on-premises without modification. Fast startup. Containers start in seconds rather than the minutes required for VM to KES, enabling rapid scaling. Resource efficiency. Containers share the host OS kernel, making them far more density efficient than vMIS. Immutability. Each release is a versioned image. Rolling back means pulling the previous tag. Ecosystem. Kubernetes, Docker Compose, Helm, and container registries, ECR Docker Hub, form a mature operational platform.
What is the 12-factor app methodology?
The 12-factor app is a set of principles for building modern, cloud-native, scalable software-as-a-service applications. Originally published by Heroku engineers, it remains the foundational reference for container and microservice design. The 12 factors. 1. Codebase. One codebase tracked in version control, many deploys. 2. Dependencies. Explicitly declare and isolate dependencies, pip, npm maven. 3. Config. Store config, credentials, ports, URLs. In environment variables, not in code. 4. Backing services. Treat databases, caches, and queues as attached resources, replaceable without code changes. 5. Build, release, run. Strictly separate the build, release, and runtime stages. 6. Processes. Execute the app as one or more stateless processes. Persist state in backing services. 7. Port binding. Export services via port binding. No app server dependency. 8. Concurrency. Scale out horizontally by running more process instances. 9. Disposability. Fast startup and graceful shutdown enable robust scaling and deployment. 10. Dev/prod parity. Keep development, staging, and production as similar as possible. 11. Logs. Treat logs as event streams. Write to a stdout and let the platform aggregate them. 12. Admin processes. Run admin tasks, migrations, scripts as one-off processes in the same environment.
How do you handle configuration management in DevOps?
Configuration management ensures all servers and environments are consistently configured and stay that way over time. Common tools. Ansible, agentless, YAML-based playbooks pushed over SSH, great for heterogeneous environments. Puppet and Chef, agent-based tools that continuously enforce desired state on managed nodes. Salt Stack, event-driven, high-performance agent-based configuration management. Key concepts. Idempotency, running a playbook multiple times produces the same result, critical for safe automation. Drift detection, tools continuously compare actual state to the desired state and alert on or autocorrect divergence. Inventory management. Maintain an up-to-date inventory of all managed hosts, static files, or dynamic cloud inventory. Role-based organization. Structure playbooks/modules into reusable roles for common concerns, web server, database, monitoring agent. In containerized environments, much of traditional config management is replaced by container image builds and Kubernetes config maps/secrets.
How do you ensure high availability in a cloud-based architecture?
High availability, HI, means designing a system so that failures of individual components do not cause service disruption. Core strategies. Eliminate single points of failure, SPOFs. Every critical component, app servers, databases, load balancers, should have redundant counterparts. Load balancing. Distribute traffic across multiple instances so no single instance is overwhelmed or becomes a bottleneck. Auto-scaling. Automatically add capacity under load and remove it when load drops, maintaining performance without over-provisioning. Multi-IZ/multi-region deployments. Spread workloads across multiple availability zones or regions so a data center-level failure doesn't take down the service. Health checks and automatic failover. Load balancers and orchestrators continuously health check instances and route around failures within seconds. Circuit breakers. Prevent cascading failures by halting requests to a degraded downstream service and failing fast. Database replication and read replicas. Synchronous or asynchronous replication ensures data durability even if the primary node fails.
What is the difference between monolithic and microservices architectures?
Monolithic architecture packages the entire application, UI, business logic, and data layer, into a single deployable unit. Advantages of monoliths: simpler development, one codebase, one process, easy end-to-end testing, no network latency between components, and straightforward deployment. Drawbacks: as the application grows, builds slow down, changes require redeploying everything. Scaling means scaling the whole application even if only one feature is under load. And a bug in any module can crash the entire process. Microservices architecture decomposes the application into independent services that communicate over APIs or message queues. Advantages: independent deployment and scaling of each service, technology flexibility, fault isolation, one service crash doesn't bring down others, and smaller, more focused teams. Drawbacks: distributed systems complexity, higher operational overhead, inter-service latency, and the need for robust observability, service discovery, and API versioning. The right choice depends on team size, domain complexity, and operational maturity.
How do you monitor microservices effectively?
Monitoring microservices requires observability tools that can correlate signals across many independently deployed services. Key approaches: distributed tracing. Tools like Jaeger, Zipkin, or a WS X-ray follow a single request as it traverses multiple services, revealing where latency or errors originate. Centralized logging. Aggregate logs from all services into a single platform, ELK Stack, Grafana Loki, Splunk, with correlation ID to KES so all events from one request can be linked. Metrics and dashboards. Prometheus scrapes service metrics. Grafana visualizes them. Use the RED method, rate, errors, duration, as a baseline for every service. Service mesh. Istio or Linkerd provides automatic mutual TLS, traffic metrics, and circuit breaking without changing application code. Synthetic monitoring. Proactively test critical user journeys from outside the system to catch issues before users report them. Alerting. Set SLO-based alerts, burn rate alerts, rather than simple threshold alerts to reduce noise.
How do you secure a CI/CD pipeline?
The CI/CD pipeline is a high-value attack surface because it has elevated access to production systems. Securing it requires defense in depth. Key controls. Least privilege access. CI runners should have only the permissions needed for their specific job, no wildcard IAM policies. Secrets management. Store credentials in a vault or the CI platform's secret store, never in environment files or plain text config. Dependency scanning. Tools like Snike, OWASP dependency check, or Dependabot flag vulnerable third-party packages on every build. SIST and container scanning. Trivy, Gripe, or Anchor scan container images for CVEs before they reach production. Code signing and artifact integrity. Sign build artifacts and verify signatures before deployment to prevent tampering. Branch protection rules. Require passing CI checks and peer review before merging to main. Pipeline as code review. Treat Jenkins file / GitHub / workflows / GitLab YAML changes with the same rigor as application code. Audit logging. Log every pipeline trigger, secret access, and deployment action for forensic analysis.
What are some common DevOps anti-patterns?
Anti-patterns are practices that seem helpful but actually impede DevOps goals. Siloed teams. When Dev, Ops, QI, and security operate independently with separate goals, handoffs create delays, finger-pointing, and slow incident response. The fix is cross-functional teams that own a service end-to-end. Manual deployments. Humans clicking through consoles or running ad hoc scripts leads to inconsistency, undocumented steps, and error-prone releases. Automate everything in the pipeline. Lack of monitoring. Deploying without observability means flying blind. Incidents are discovered by angry users rather than by your own alerts. Ignoring security. Bolting security on at the end creates expensive rework and vulnerabilities in production. Shift security left into development and the pipeline. Long-lived feature branches. Branches that diverge for weeks cause painful merges and delay feedback. Use trunk-based development with short-lived branches. Not testing in production-like environments. Differences between staging and production cause it worked in staging failures. Invest in environment parity.
How do you implement DevSecOps?
DevSecOps integrates security practices into every phase of the software development and delivery lifecycle, rather than treating it as a separate, end-of-process gate. Phase-by-phase integration. Plan. Conduct threat modeling during design. Include security acceptance criteria in user stories. Code. Use IDE plugins, SonarLint, for real-time feedback. Enforce secure coding standards via code review checklists. Build, run SIST, Sonar Quebe checkmarks, and dependency scanning, SNIKE OWASP dependency check, on every commit. Test, include DIST, OWASP ZIP, burp suite, and fuzz testing in the test stage. Release, scan container images with Trivy or Gripe, enforce policy as code gates, OPA. Deploy, use secrets management, enforce least privilege IAM roles, and validate infrastructure configs with tools like Chekhov. Operate, continuous vulnerability scanning, anomaly detection, SIEM, and regular penetration testing.
What is a service level agreement, SLA?
A service level agreement is a formal contract between a service provider and a customer that defines the expected level of service and the consequences if that level is not met. Common SLA metrics, availability/uptime. For example, 99.9%, 3 nines, equals no more than -8.7 hours of downtime per year. 99.99% equals -52 minutes per year. Response time, maximum latency for IPI calls or support ticket acknowledgement. Recovery time objective, RTO, maximum acceptable time to restore service after an outage. Recovery point objective, RPO, maximum acceptable data loss measured in time. SLAs typically include financial penalties, service credits, for violations which create a direct accountability mechanism. Internally, teams set SLOS, service level objectives, stricter targets than the SLA, so there is a buffer between internal thresholds and the contractual commitment.
How do you ensure compliance in DevOps?
Compliance means demonstrating to auditors and regulators that your systems and processes meet defined standards: GDPR, SOC2, PCI-DSS, HIPAA, ISO 27001. DevOps approaches to compliance. Policy as code. Encode compliance rules in tools like Open Policy Agent, OPA, HashiCorp Sentinel, or AWS config rules so they are automatically enforced rather than manually checked. Automated audit trails. Every pipeline run, deployment, and config change is logged with timestamps and actor identity. The audit log is produced as a byproduct of normal operations. Infrastructure compliance scanning. Chekhov, Teraskin, or AWS Security Hub continuously evaluate IIC templates and cloud resources against compliance benchmarks, CIS, NIST. Immutable records. Store logs and audit evidence in tamper-evident, append-only storage. Access reviews. Automate regular reviews of IAM roles and permissions to detect privilege creep. Separation of duties. Use pipeline approvals to enforce that no single person can both write and deploy code to production.
What is a chaos engineering experiment?
Chaos engineering is the discipline of deliberately injecting failures into a system in a controlled way to expose weaknesses before they cause real outages. The process. 1. Define steady state. Establish what normal looks like baseline metrics such as error rate, latency, and throughput. 2. Hypothesize. Predict that the system will remain in steady state despite a specific failure. 3. Inject failure. Terminate instances, inject network latency, exhaust CPU, or cut off a dependency. 4. Observe. Monitor whether steady state is maintained or degraded. 5. Learn and fix. If steady state is broken, identify the root cause and harden the system. Famous examples: Netflix's Chaos Monkey, random instance termination, and Chaos Kong simulates an entire AWS region outage. Chaos experiments should start in lower environments, be time-boxed, and have a clear abort condition to minimize blast radius.
How do you reduce deployment downtime?
Zero downtime deployments require combining the right deployment strategy with database and infrastructure best practices. Strategies: rolling updates. Replace instances incrementally. The load balancer keeps healthy instances serving traffic throughout. Blue-green deployment. Switch traffic atomically to the new environment. Rollback is instant. Canary releases. Shift a small percentage of traffic first. Promote only after metrics confirm health. Supporting practices: backward-compatible API changes. Add fields before removing them. Version APIs to avoid breaking existing clients. Expand contract database migrations. Add the new column/table first, migrate data, then remove the old schema. Each step is independently deployable. Feature flags. Deploy the code change decoupled from activating the feature. Health checks. Ensure orchestrators only route traffic to fully initialized instances. Connection draining. Gracefully finish in-flight requests before terminating old instances.
How do you handle database migrations in CI/CD?
Database schema changes are one of the riskiest parts of a deployment because they are often irreversible and can break running application instances. Best practices: use a migration tool, Flyway, Liquibase, Alembic, Python, or Active Record Migrations, Rails. Version and apply schema changes as code tracked alongside application code. Migrations run automatically in the pipeline before or during the new app version starts. Forward-only migrations. Prefer additive changes, add column, add table. Over destructive ones, drop column, rename. Keep schema and application code backwards compatible through a multi-step expand contract process. Test in staging first. Always run migrations against a production-sized dataset in staging before production. Rollback plan. Have a tested-down migration or a data snapshot available for the rare case that a migration must be reversed. Never run destructive changes automatically. Dropping columns or tables should require an explicit, separate deployment after the old code version is fully retired.
What is an API gateway, and why is it used?
An API gateway is a managed entry point that sits in front of a collection of backend services, typically microservices, and handles cross-cutting concerns centrally. Core functions: request routing. Directs incoming requests to the appropriate downstream service based on path, headers, or method. Authentication and authorization. Validates tokens, JWT, OAuth 2.0, and enforces access policies before requests reach services. Rate limiting and throttling. Protects backend services from traffic spikes and abuse. SSL termination. Decrypts HTTPS at the gateway, reducing complexity in downstream services. Request/response transformation. Adapts payloads, adds headers, or aggregates responses from multiple services. Observability. Centralizes logging, tracing, and metrics collection for all inbound traffic. Caching. Returns cached responses for repeated read requests, reducing backend load. Popular gateways: AWS API Gateway, Kong, Nginx, Apigee, and Traefik.
How do you implement infrastructure testing?
Infrastructure testing validates that IIC code provisions the correct, secure, and compliant resources before those resources reach production. Testing levels. Static analysis/linting. Validate syntax and flag misconfigurations before any resources are created. Tools: tflint, Terraform, cfnlint, CloudFormation, yamlint, Chekhov. Unit tests for modules. Test individual Terraform modules or Ansible roles in isolation using terratist, Go-based, or molecule, Ansible. Integration tests. Actually provision resources in an ephemeral test account, run assertions, and then destroy them. Terratist and Kitchen Terraform support this pattern. Compliance tests. Inspect and OpenSCAP validate that provisioned resources meet security baselines, CIS benchmarks. Policy as code gates. Open Policy Agent, OPA. Rules block non-compliant resource definitions in the CI pipeline. Best practice. Run all tests in a dedicated, isolated cloud account or namespace to avoid affecting shared environments.
How do you manage multi-cloud deployments?
Multi-cloud means running workloads across 2 or more cloud providers, AWS, Azure, GCP, for redundancy, cost optimization, or avoiding vendor lock-in. Challenges: each provider has different IPIs, IAM models, networking primitives, and managed services. Without abstraction, you end up with duplicated, provider-specific automation. Strategies: cloud-agnostic IIC. Terraform supports all major providers through a consistent HCL syntax and state model, making it the de facto standard for multi-cloud provisioning. Container orchestration. Kubernetes abstracts away the underlying cloud, making workloads portable across providers. Unified secrets management. HashiCorp Vault can manage secrets across all clouds from a single plane of control. Service mesh. Istio or Console Connect provides consistent traffic management, mutual TLS, and observability across clusters in different clouds. Centralized observability. Aggregate metrics, logs, and traces from all providers into a single platform, Datadog, Grafana Cloud. Cost management. Use FinOps tools, Cloud Health, Apptio Cloudability, to track and optimize spending across providers.
What is the difference between SLO and SLI?
SLI, Service Level Indicator. A specific, measurable metric that quantifies one aspect of a service's behavior from the user's perspective. Examples of SL is request success rate, percentage of HTTP requests returning 2xx, latency, percentage of requests served under 200 ms, throughput, requests per second, or availability, percentage of time the service responds to health checks. SLO, Service Level Objective, a target value or range for an SLI over a defined time window. Example: 99.9% of requests will succeed over a rolling 30-day window, or 95% of requests will complete in under 200 ms. Error budget, the allowed margin of failure derived from the SLO. If your SLO is 99.9% availability, your error budget is 0.1%, about 43 minutes of downtime per month. When the error budget is exhausted, the team pauses feature work and focuses on reliability. SLA, Service Level Agreement. The contractual, customer-facing commitment, typically less ambitious than internal SLOS, to provide a buffer.
How do you manage dependencies in DevOps?
Dependency management covers both direct third-party libraries your code uses and their transitive dependencies. Language-specific managers. Python, pip with requirements.txt or poetry with piproject.toml. Node.js, npm or yarn with packagelock.json/yarnlock. Java/Kotlin, Maven, POM.xml, or Gradle, build Gradle. Go modules with GoSum for cryptographic verification. Best practices. Lock files. Commit lock files to version control so every build uses identical dependency versions, preventing "it worked yesterday" surprises. Automated vulnerability scanning. Snike, OWASP dependency check, or GitHub Dependabot scan dependencies on every commit and open pull requests for vulnerable packages. Automated updates. Dependabot or Renovate bot open prtks to update dependencies regularly, keeping them fresh without manual effort. Private artifact repositories. Nexus, Artifactory, or a WS Code artifact mirror external packages internally for availability and security control. License compliance. Tools like FOSS detect incompatible open source licenses before they become legal issues.
How do you handle rollback in a Kubernetes environment?
Kubernetes tracks deployment history and provides built-in rollback mechanisms. Revert to the previous replica set.
Code kube control rollout undo deployment /name.
Roll back to a specific revision.
Code kube control rollout undo deployment /name to revision equals n.
View rollout history.
Code kube control rollout history deployment /name.
Kubernetes keeps a configurable number of old replica sets, controlled by revision history limit, so previous versions are available. GitOps rollback. In a GitOps workflow, Argo CD flux. Rollback is a git revert to a previous commit. The operator reconciles the cluster back to that state automatically, providing a clean audit trail. For stateful applications, ensure database migrations are backward compatible before the rollout, so that reverting the application doesn't leave the database in an incompatible state.
What are the best practices for writing Docker files?
Well-written Docker files produce smaller, more secure, and faster building images. Key practices. Use lightweight base images. Prefer Alpine-based, for example, Python 3.12 Alpine, or distroless images over full OS images to minimize attack surface and image size. Multi-stage builds. Use separate build and runtime stages. The final image contains only the compiled artifact and runtime dependencies, not compilers, source code, or dev tools. Minimize layers. Chain-related run commands with and to reduce the number of layers and avoid caching intermediate bloat. Order instructions by change frequency. Put rarely changing instructions, from run apt-get install, near the top so Docker can cache them, and frequently changing ones, copy. Near the bottom, never hardcode secrets. Don't copy and files or set env with credentials. Use runtime secret injection instead. Run as a non-root user. Add a dedicated user and switch to it with user to follow the principle of least privilege. Pin base image versions. Use explicit tags Python 3.12.3 Alpine 3.19 rather than latest to ensure reproducible builds. Add a Docker ignore file. Exclude Git, node modules, test files, and build artifacts to keep the build context small.
What is FinOps in cloud computing?
FinOps, financial operations, is a cultural practice and organizational framework that brings engineering, finance, and business teams together to take joint accountability for cloud spending. Core principles: visibility. Tag every resource by team, product, and environment. Use dashboards, AWS Cost Explorer, Grafana, Cloud Health, to give teams real-time spend visibility. Accountability, showback, showing teams their cost, and chargeback, billing teams for their usage. Create cost awareness and ownership. Optimization levers. Right sizing. Match instance sizes to actual CPU/memory usage rather than over-provisioning. Reserved instances /savings plans. Commit to 1 or 3 year terms for predictable workloads for up to 72% savings. Spot/preemptible instances. Use for fault-tolerant batch workloads at 60-90% discount. Auto-scaling. Scale in when load is low, don't run idle capacity. Lifecycle policies. Automatically archive or delete old S3 objects, snapshots, and logs. Process. Establish a regular cloud cost review cadence, weekly or bi-weekly, with engineering leads.
How do you implement policy as code in DevOps?
Policy as code means expressing compliance and security policies as executable code that is version-controlled, automatically evaluated, and enforced in the pipeline rather than relying on manual audits or documentation. Key tools: Open Policy Agent, OPA, a general-purpose policy engine that evaluates Rego language policies. Used to validate Kubernetes admission requests, Terraform plans, IPI authorization, and more. HashiCorp Sentinel, a policy framework built into Terraform Cloud/Enterprise that evaluates policies at planned time before any infrastructure is created. Chekhov scans IIC files, Terraform, CloudFormation, Helm Docker files against hundreds of built-in security and compliance checks. Kyverno, a Kubernetes native policy engine that validates, mutates, and generates resources without requiring Rego. Implementation pattern: 1. Write policies as code in version control alongside application code. 2. Run policy checks in the CI pipeline as a blocking gate, fail the build on violations. 3. Enforce at runtime via admission controllers, OP a gatekeeper, Kyverno, in Kubernetes. 4. Report compliance posture continuously to a dashboard for audit evidence.
How do you handle incident response in DevOps?
Effective incident response minimizes the duration and impact of production issues and builds organizational learning from every event. Key elements: on-call rotation, clearly defined, evenly distributed on-call schedules with escalation paths. Tools: PagerDuty, OpsGenie, VictorOps. Runbooks, pre-written, step-by-step guides for known failure scenarios so responders don't have to improvise under pressure. Incident severity levels, P1, P4. Define criteria for each level to ensure proportionate response. War Room/incident channel, a dedicated Slack channel or bridge call where responders, leads, and communicators coordinate. Clear roles: incident commander owns the response, technical lead diagnoses and fixes, communications lead keeps stakeholders updated. MTTR focus: track mean time to detect, MTTD, and mean time to recover, MTTR, as key reliability metrics. Blameless postmortems: after resolution, hold a structured review to find root causes and systemic improvements without assigning personal blame. Document findings and action items.
What is Site Reliability Engineering, SRE?
SRE is a discipline pioneered by Google that applies software engineering principles to the problems of infrastructure and operations, with the explicit goal of building and running large-scale, reliable distributed systems. Core SRE concepts: SLOS and error budgets define target reliability, for example, 99.9% availability. The gap between 100% and the SLO is the error budget. When the budget is spent, reliability work takes priority over feature work. Toil reduction: repetitive, manual, automatable operational work should be continuously identified and eliminated. SREs aim to keep toil below 50% of their time. 4 golden signals: latency, traffic, errors, and saturation are the primary metrics every service should expose. Blameless postmortems: psychological safety encourages engineers to surface failures honestly, leading to systemic improvements. Eliminating silos: SREs are embedded with development teams and share responsibility for production reliability, breaking the traditional dev/ops wall. CRE, Customer Reliability Engineering, extends SRE principles to help customers run their own systems reliably.
How do you enforce security compliance in a DevOps pipeline?
Security compliance enforcement in a pipeline means automating checks so that non-compliant code, dependencies, or infrastructure never reach production. Layers of enforcement: pre-commit hooks, run secret detection, get secrets, pre-commit hooks with detect secrets, and linting locally before code is even pushed. SIST in CI, Static Application Security Testing Tools, Sonar Quebe, Checkmarks, SemGrep. Scan source code for vulnerability patterns on every pull request. Dependency scanning. Snike, OWASP dependency check, or GitHub Dependabot flag vulnerable packages and block merges above a configurable severity threshold. Container image scanning. Trivy or Gripe scan images for OS and application CVEs as part of the build stage. IIC compliance checks. Chekhov, TFSec, or Terrascan validate Terraform and CloudFormation templates against CIS benchmarks. Policy gates. OP or Sentinel enforce custom compliance rules at plan/apply time, blocking non-compliant infrastructure changes. Runtime compliance. A WS config, Azure policy, or GCP Security Command Center continuously monitor live resources and alert on drift.
How do you manage hybrid cloud environments?
A hybrid cloud connects on-premises infrastructure with one or more public clouds, enabling workloads to span both environments seamlessly. Management challenges. Inconsistent tooling, networking, identity, and operational processes across environments. Key tools and approaches. Unified control planes. Google Anthos, Azure Arc, and AWS Outposts extend cloud management APIs to on-premises hardware, allowing consistent policy, monitoring, and deployment from a single pane of glass. Infrastructure as code. Terraform manages resources on-premises, VMware, bare metal, and in public clouds with a single workflow. Container orchestration. Kubernetes clusters running on-premises and in the cloud can be federated, enabling workload portability. Networking. VPNs, AWS Direct Connect, or Azure Express Route provide private, low-latency connectivity between on-premises data centers and cloud VPC-to-CAS. Unified identity. Extend Active Directory or an IDP, Okta, ping, to cover cloud resources, avoiding separate identity silos. Centralized observability. Aggregate metrics and logs from both environments into a single monitoring platform.
What is an SBOM, software bill of materials?
An SBOM is a formal, machine-readable inventory of all components, open-source libraries, third-party packages, internal dependencies, and their versions contained in a software artifact. Why SBOMs matter? Vulnerability management. When a CVE is disclosed, for example, log4shell. An SBOM lets you instantly answer, does any of our software use log4j and which version? Across your entire portfolio. Supply chain security. Executive Order 14028, U.S. Government, 2021, mandated SBOMs for software sold to federal agencies, signaling broad industry adoption. License compliance. SBOMs surface open-source licenses in use, helping legal teams identify copyleft obligations. Audit evidence. Regulators and enterprise customers increasingly request SBOMs as part of procurement and compliance reviews. Standard formats, SPDX Linux Foundation and Cyclone DX OWASP are the two dominant SBOM formats. Generate an SBOM for a container image with SIFT.
Code SIFT Engine X, latest O Cyclonix JSON SBOM JSON, Gripe SBOM, /SBOM JSON.
Tools, SIFT generates SBOMs from container images. Gripe, vulnerability scanning using SBOMs. Snike and Trivy all support SBOM generation and consumption.
How do you implement auto-remediation in DevOps?
Auto-remediation means the system detects an issue and automatically takes corrective action without requiring human intervention, reducing MTTR, mean time to recover, dramatically. Common patterns, self-healing infrastructure. Kubernetes restarts crashed containers, replaces unhealthy nodes, and reschedules pods automatically via liveness and readiness probes. Auto-scaling. When CPU or memory thresholds are breached, Autoscalers, Kubernetes HPI/VPI, AWS auto-scaling groups. Add or remove capacity. AWS Lambda remediation. CloudWatch alarms trigger Lambda functions that take corrective actions, for example, automatically stopping an over-budget instance or revoking an overly permissive security group rule. Ansible auto-remediation. IWX or Ansible Tower can trigger playbooks in response to alerts, for example to restart a failed service or free up disk space. Kubernetes operators. Custom operators encode operational knowledge to handle complex remediation workflows, for example, automatically performing a database failover. Runbook automation. Tools like PagerDuty Runbook Automation or Rundeck execute pre-approved remediation runbooks automatically when specific alert conditions are met. Key consideration. Implement careful safety boundaries. Auto-remediation should require a human approval gate for destructive actions and should log every action for auditability.
How do you secure a Kubernetes cluster?
Kubernetes clusters have a broad attack surface. Defense in depth across the control plane, network, workloads, and supply chain is required. Key controls. RBAC, role-based access control. Grant users and service accounts only the minimum permissions they need. Avoid cluster admin bindings for non-platform engineers. Network policies. Use Kubernetes network policy resources enforced by a CNI like Calico or Cilium to restrict pod-to-pod communication. Default deny all traffic and explicitly allow only required paths. Pod security admission, PSI. Enforce pod security standards, baseline or restricted, to prevent privileged containers, host network access, and host path mounts. Secrets management. Avoid storing sensitive values in etcd as plain Kubernetes secrets. They are only base 64 encoded. Integrate with HashiCorp Vault or use sealed secrets with encrypted storage. Image security. Only pull images from trusted registries. Enforce image signing, cosign/notary, via an admission controller. Scan images with Trivy before deployment. Rotate TLS certificates. Use Cert Manager to automate certificate issuance and rotation for internal cluster communication. etcd encryption. Enable encryption at rest for etcd to protect secrets stored in the cluster's backing data store. Audit logging. Enable Kubernetes IPI server audit logging to record all control plane operations for forensic analysis. Runtime security. Tools like Falco Monitor System, calls at runtime, and alert on suspicious container behavior.
How do you optimize cloud costs in a DevOps environment?
Cloud cost optimization is an ongoing engineering discipline, not a one-time project. Visibility first. Tag every resource by team, environment, and application so costs can be attributed accurately. Use native cost dashboards, AWS Cost Explorer, Azure Cost Management, GCP cost reports, and set budget alerts to catch unexpected spend. Right-sizing. Analyze CPU, memory, and network utilization. Downsize over-provisioned instances. AWS Compute Optimizer and Azure Advisor provide automated recommendations, commitment-based discounts. Use reserved instances or savings plans for stable, predictable workloads, up to 72% savings versus on-demand. Use spot/preemptible instances for fault-tolerant batch jobs, CI runners, or stateless workloads, 60–90% savings. Auto-scaling. Scale in aggressively during off-peak hours. Schedule scale down for development and staging environments overnight and on weekends. Storage and data transfer. Apply S3 lifecycle policies to transition old objects to cheaper storage tiers, Glacier, or delete them. Minimize cross-region and cross-IZ data transfer, which often surprises teams with high costs. Continuous improvement. Hold regular FinOps reviews with engineering leads to review anomalies, act on recommendations, and celebrate wins.
What is environment parity, and why does it matter?
Environment parity means keeping development, staging, and production as similar as possible to reduce works on my machine issues. Use identical OS, dependencies, and configurations across environments. Containers and IIC tools help enforce parity automatically.
What is toil in SRE, and how do you reduce it?
Toil is manual, repetitive, automatable work that scales linearly with service growth. Reduce toil by automating runbooks, self-healing infrastructure, and eliminating manual deployment steps. SRE teams aim to keep toil below 50% of their work.
What is ChatOps, and how does it benefit DevOps teams?
ChatOps integrates operational workflows into chat platforms like Slack or Microsoft Teams using bots. Teams can trigger deployments, check status, and respond to incidents directly from chat. It improves visibility, collaboration, and faster incident response.